Hi, my name is Aimee Barciauskas, and I'm a cloud and data engineer at Development Seed, where I've been working for the past 7 years with NASA on its migration to the cloud. I'll be presenting on cloud-native data cubes with Zarr, and more specifically how we can provide sea surface temperature analysis with a method called virtual Zarr. If you would like to follow along with slides that go along with this presentation, please follow the More Details link at the top of this poster. So first of all, I'd like to thank my collaborators at EarthMover, PODAC, and NASA's Impact Program for supporting this work. So the background for this work is that users need direct access to analysis-ready data cubes, not individual files. Current methods to deliver data cubes require extensive user processing and organization. However, now there are new methods, which we'll demonstrate in this presentation, which enable creating cloud-optimized data cubes using references to data chunks in the original files. And I'll talk a little bit about what that means in a few slides. So we use Zarr as the cloud-optimized specification for storing multidimensional data sets. We use Zarr, which is a Python library, to parse Zarr metadata and chunk references from the original netcdf files. And then we used IceChunk, which is a storage engine and format for storing data in both native Zarr and virtual references. And we needed to do both of those things for this data set. So again, Zarr is a cloud-native specification for multidimensional data. And the metadata specification defines stores, hierarchies, groups, arrays, dimensions, and more. And we used Zarr to create references to chunks in the original files. So rather than reformatting and reprocessing and restoring the data in the original netcdf files, we use Zarr to understand the byte ranges for different coordinate chunks. So in this example, you see how there is, for the first chunk of analyzed SST data, a path, an offset, and a length to one of the chunks. And the chunk metadata stores this for every chunk in the whole data set. So again, Zarr enables parsing various file formats from netcdf to geotiff to HDF5 to extract and generate valid Zarr metadata and chunk references. Zarr exposes a friendly X-ray API that can be used to work with these virtual dataset objects, such as to concatenate datasets from various files. Zarr also supports storing these virtual references so they can be read back out and reused. And it can store those virtual references as CurChunk JSON, Parquet, or IceChunk. IceChunk is the storage engine for our arrays. It's based on the Zarr data model, and it provides operational and versioning features such as ACID transactions, versioning, branching, and garbage collection. So we use these methods to generate a virtual Zarr data cube for the Mir SST dataset. Our goals were to develop a workflow for creating the data cube using the original netcdf files, expose and work around issues in the underlying data files, understand the performance of both writing and reading this data set, and compare the virtual store read performance with reading from the original files. In a notebook that is available through the slides, you'll see that there is a demonstration of how to read this data set using Zarr Python. And in that notebook, we're able to read a 1 degree by 1 degree grid cell for over 21 years of daily data in under 40 seconds. This represents fetching over 77 million data points from the original netcdf files. And we wanted to compare this with reading data from the original files using X-ray. We weren't able to actually do the same thing of reading data for the whole 21 years in a reasonable amount of time. So we looked at how long it would take just to open 1 month of data, which is about 31 files, load and plot 1 degree by 1 degree for just 1 month as opposed to over the whole 21 years. In this exercise, we're able to compare the throughput by comparing the process of Zarr Python with the ice chunk store, which is able to read 7,736 granules in 39 seconds, versus using the original files with X-ray open multi-file dataset, which was able to open and read data from 31 granules in 46 seconds. This represents a over 250 times greater throughput for the ice chunk store using Zarr Python versus the original files. With the ice chunk store, we're able to read from 198 granules per second versus less than 1 granules per second using the original files. As for dataset generation cost, we wanted to note that all of this work is has very minimal expense. We estimate that creating the dataset cost about $1.23 using a serverless architecture, and storing the data, which includes the ice chunk artifacts as well as some native Zarr data, cost about $4. We used a serverless architecture to generate the reference data and the Zarr data. We used an open source system called lithops to parallelize the function of opening the virtual datasets and then concatenating them and writing them to ice chunk. We used a similar process for writing native Zarr for the dates that required writing native Zarr when there were inconsistencies in the data. So this architecture is very similar but requires more parallelization as we were writing actual native data in native Zarr format. And all of these projects that I mentioned are open source, so you can learn much more and try them out for yourselves. The Zarr documentation is available at zarr.dev. The virtualized Zarr documentation is available at virtualizeZarr.readthedocs.io, and the ice chunk docs are at icechunk.io. There's also a great blog post about this work from Earthmover at earthmover.io/blog/NASA-icechunk. That blog post goes into these same methods but used for the GPM iMerge dataset. And there's documentation for this specific project at github.com/earth-mover/icechunk-nasa. Thank you for your time.